Imagine being told your entire life that the universe began in a single fiery moment, that all of space, time, matter, and energy erupted from a point smaller than an atom, and that since then everything has followed a predictable script of expansion, cooling, and gradual organization. That's the story written into textbooks, the narrative that earned Nobel Prizes, and the version of reality most of us never thought to question. But what if that story is incomplete? What if the most powerful telescope ever built has revealed cracks in the foundation of our cosmic history, so deep that the very beginning of time itself may need to be rewritten? That's exactly what the James Webb Space Telescope is doing, and the results are nothing short of staggering. Launched after 3 decades of planning and a $10 billion investment, Webb was designed to be our ultimate time machine, peering back across billions of years to show us the earliest moments after the Big Bang. Scientists expected to find small, messy galaxies still learning how to take shape, filled with primitive stars that had only just begun burning hydrogen. Instead, Webb is sending back images that feel like science fiction made real. Massive, mature galaxies blazing with billions of stars, enormous black holes that somehow ballooned to impossible sizes in record time, and mysterious light sources shining in an era when the universe was supposed to be completely dark. Each discovery doesn't just add a new detail to the story, it flips entire chapters upside down. Think of it like opening a baby photo album and finding pictures of a fully grown adult staring back at you. That's what Webb revealed about the early universe. Where astronomers expected fragile beginnings, they found shocking maturity. Galaxies that should have taken billions of years to form appeared just a few 100 million years after the supposed birth of the cosmos, fully developed and organized. Black holes, weighing billions of times more than the Sun, existed when the universe was still an infant, even though by every law of physics they should have needed far more time to reach that size. The telescope's infrared eyes pierced through cosmic dust and distance to expose structures that look like they've skipped ahead in time, as if someone pressed fast forward on cosmic evolution. Every piece of data forces scientists to confront an uncomfortable truth. Maybe we don't have the first page of the universe's story right at all. This isn't just about 1 or 2 strange objects. It's about a systematic pattern of impossibilities piling up, each one more dramatic than the last. We're seeing galaxies too massive, stars too bright, and chemical elements appearing far too early in history. The timeline we've trusted for decades doesn't fit anymore. For years, cosmology has been guided by the Big Bang model and its carefully calculated sequence of events. First came the explosive beginning, then cooling, then the slow formation of stars and galaxies. But Webb's discoveries don't line up with that recipe. It's as if the universe decided to ignore its own rulebook, accomplishing in a few 100 million years what should have taken billions. And the strangest part, every new Webb observation seems to deepen the mystery rather than resolve it. Instead of writing the final chapter of the story of cosmic origins, this telescope is showing us that the real story might be far stranger, far older, and far more complex than we ever dared to imagine. The James Webb Space Telescope was never meant to create controversy. It was built as a successor to the Hubble, a powerful eye in the sky designed to confirm, refine, and extend what we thought we already knew about the birth of the cosmos. At a cost of $10 billion, and after 30 years of design setbacks and engineering triumphs, Webb was hailed as humanity's most ambitious scientific machine. Its primary purpose was simple on the surface, but profound in scope. To look back through time to the very dawn of the universe, to see the first galaxies flicker into existence after the Big Bang, and to provide the most detailed portraits of cosmic infancy ever captured. Scientists expected Webb to show them fragile beginnings, small, faint galaxies, just barely coalescing out of a chaotic early universe, clusters of primitive stars that hadn't yet had time to evolve, and structures so immature they would look like cosmic toddlers stumbling through their first steps. The goal wasn't to challenge the Big Bang story, but to put the final seal of confirmation on it, to show us in vivid detail the stages of growth our theories already predicted. The telescope itself is a marvel of engineering that speaks to human persistence and ingenuity. With a mirror 21 feet across, Webb gathers more light than any instrument ever launched, and its location 1 million miles from Earth shields it from the interference of our planet's heat and light. Unlike Hubble, which looked mostly invisible and ultraviolet wavelengths, Webb peers into the infrared, allowing it to pierce through the thick clouds of cosmic dust that have hidden much of the early universe from view. This ability effectively transforms Webb into a time machine, pulling back the curtain on epochs of cosmic history that have remained invisible for billions of years. The light it captures has traveled across space for over 13 billion years, meaning that every image is a direct glimpse into the past, into a universe only a fraction of its current age. But as soon as Webb's golden mirrors began sending data back to Earth, the surprises started piling up, and they weren't the kind scientists had prepared for. Instead of confirming expectations, Webb shattered them. The galaxies it revealed weren't the tiny, fragile structures of theory. They were massive, complex, and organized, their stars blazing brightly, their forms surprisingly mature for such an early period. To use an analogy, it was like expecting to find a nursery filled with infants, and instead stumbling into a city already bustling with adults, skyscrapers, and infrastructure. The universe that Webb showed us didn't look like a young cosmos, just getting started. It looked like one that had somehow skipped entire stages of growth, leaping ahead in a timeline that shouldn't have allowed it. This fundamental contradiction has left cosmologists scrambling. Webb's purpose was to give us clarity, to provide the missing puzzle pieces of cosmic origin, but instead it has revealed that the puzzle itself may not fit the picture we've been trying to assemble. Its mission has become both validation and provocation, confirming the telescope's power while simultaneously undermining the very theories it was built to support. Every image is both breathtaking and unsettling, a reminder that the universe is under no obligation to follow our expectations. In that sense, Webb has fulfilled its purpose in a way no one anticipated. It hasn't just opened a window into the past, it has opened a door to rewriting the most fundamental story we've ever told about existence. When scientists first began combing through Webb's earliest deep-field images, they expected to catalogue small, faint galaxies, clumps of stars just beginning to take shape in a universe still recovering from the chaos of the Big Bang. Instead, what they found was something closer to a cosmic horror story for the standard model of cosmology. Amid the thousands of tiny smudges scattered across the deep field were 6 glowing red points, seemingly ordinary at first glance, until astronomers calculated their distance and age. These objects existed just 500 to 700 million years after the supposed beginning of the universe, an era when conditions should have been too hot, too unstable, and too chemically primitive to allow the birth of anything but the simplest star clusters. And yet, the galaxies Webb had revealed were not small or primitive. They were massive, mature, and bursting with billions of stars, as though entire cosmic cities had been built in the time it should have taken just to clear the construction site. To put this into perspective, think of a forest. We know from observation that a forest takes at least a century to grow from seedlings into towering trees. But imagine stepping into what should be a young, barely sprouting patch of land, only to find enormous redwoods already reaching hundreds of feet into the sky. That is what Webb uncovered in the early cosmos, Galaxies that should not exist because they appear too developed, too luminous, and too massive for the time they had to form. According to standard cosmological models, it should take billions of years for galaxies to accumulate the raw material, form stars, and organize themselves into the grand spirals and ellipticals we see today. Yet here they were, fully mature in less than 1 billion years, mocking our carefully calculated timelines. The problem isn't just one of scale, it's one of physics. Building a galaxy is a step-by-step process that requires enormous amounts of time. First, dark matter clumps together to form a gravitational skeleton. Then, ordinary gas cools and collapses into this framework, giving birth to stars. Those stars live out their lives, with the most massive ones exploding as supernovae, seeding the environment with heavy elements like carbon and iron. Only then can more complex stars and planets begin to form, slowly enriching and shaping the galaxy over billions of years. Webb's galaxies seem to have fast-forwarded through this entire process, skipping steps and arriving fully grown at a time when the universe itself should barely have cooled down from its initial fireball. Each of these galaxies shines with the light of billions of suns, which implies masses larger than the Milky Way. This is perhaps the most shocking revelation, because our own galaxy has had over 13 billion years to grow into its current form, and yet these ancient systems matched or even exceeded its scale in less than 1 billion years. It would be like finding a toddler who weighs more than a full-grown adult. A biological impossibility that defies everything we know about growth and development. For galaxies, this timeline mismatch doesn't just stretch the limits of physics, it breaks them. The discovery of these early giants has triggered what researchers are cautiously calling a crisis in cosmology. If these galaxies are as massive as they appear, then our entire model of how the universe evolved may be fundamentally flawed. Perhaps the processes that govern star and galaxy formation in the early universe were radically different from those we see today. Perhaps dark matter behaved differently, or exotic physics we haven't yet discovered accelerated the growth of structures in ways we cannot yet explain. Or more provocatively, perhaps the timeline of the universe itself, the age we assign to it, the way we interpret redshift, and the very framework of the Big Bang needs to be reconsidered. Whatever the explanation turns out to be, Webb's early galaxies represent a profound challenge to our understanding of cosmic history. They are not just outliers or statistical flukes. They are systematic contradictions, consistent across multiple observations and confirmed by independent research teams. Each new image strengthens the case that the early universe was far more developed, active, and organized than we believed possible. And this is only the beginning, because behind the mass and maturity of these galaxies lies an even stranger mystery: how they could have converted their raw material into stars with an efficiency that pushes the limits of physics itself. When scientists looked closer at the massive galaxies revealed by Webb, they noticed something even more astonishing than their unexpected size and maturity. These galaxies had managed to convert their raw hydrogen and helium gas into stars with an efficiency that seems to break the rules of physics as we understand them. In the modern universe, galaxies are notoriously inefficient at turning gas into stars. Typically, only about 10% of the available gas ends up as stars, while the rest gets blown away by powerful stellar winds, violent supernova explosions, and the energy feedback that massive young stars pump into their environments. Think of it like trying to build a fire in a storm. Most of your wood and kindling gets scattered before it can burn, and only a fraction actually ignites into flame. This inefficiency is not a bug, it's a feature of the physics governing star formation. Exploding stars blast energy into their surroundings, heating gas and preventing it from collapsing into new stars, effectively putting a natural cap on how quickly galaxies can grow. Yet Webb's observations suggest that in the earliest epoch of the universe, galaxies somehow ignored this universal limitation. The galaxies Webb detected just 500 to 700 million years after the Big Bang appear to have converted nearly all of their available gas into stars, operating at close to 100% efficiency. That would be like running a factory where every single atom of raw material goes into the final product with zero waste, something no process in nature ever achieves. This perfect efficiency would mean that galaxies in the early universe found a way to suppress or completely avoid the feedback mechanisms that limit star formation in today's cosmos. Massive stars would have had to form, burn, and die without their supernova blasts dispersing the gas. Stellar winds would have had to lose their power, allowing gas to collapse undisturbed. The environment itself would have needed to operate under entirely different physical rules than what we see today. Imagine filling a bucket with water while someone constantly drills holes into its base. Normally, most of the water leaks out before the bucket fills. That's the modern universe, where gas is lost to winds and explosions before it can form stars. But in these early galaxies, the bucket had no holes. Every drop of gas collapsed into stellar material, creating vast star systems in impossibly short timescales. To make matters even more perplexing, the sheer brightness of these galaxies indicates that they contained not just many stars, but many massive, hot stars burning at peak luminosity. These stars live fast and die young, meaning entire stellar generations would have had to form, live, and explode within a cosmic instant. The efficiency problem points toward one of two unsettling possibilities. Either our models of star formation are incomplete, missing some key process that allowed early galaxies to bypass the normal bottlenecks, or the early universe itself played by different rules. Perhaps the density of matter, the chemistry of pristine gas, or even the behavior of dark matter and gravity created conditions that favored hyper-efficient star birth. Some researchers even suggest that unknown physics, new forces or particles that no longer operate today might have tipped the balance in favor of rapid and complete star formation. If true, it would mean the early universe was a kind of cosmic laboratory where matter behaved in ways fundamentally alien to our current experience. What makes this even harder to explain is that these galaxies weren't rare exceptions. Webb is uncovering them again and again, implying that hyper-efficient star formation was the rule rather than the anomaly in the infant cosmos. The numbers don't just stretch our models, they shatter them. Our cosmic timeline assumes that galaxies grow slowly, taking billions of years to build their structures through small incremental steps. Instead, Webb shows us entire stellar civilizations appearing almost overnight, as though someone pressed fast forward on the universe's evolution. And just when this efficiency paradox seems impossible enough, a deeper problem emerges at the very heart of these galaxies: the presence of supermassive black holes that defy everything we know about how fast such cosmic monsters can grow. At the very heart of these ancient galaxies lies a discovery that pushes the boundaries of what we thought was possible in cosmic evolution: supermassive black holes that already weigh billions of times more than our Sun, existing when the universe was less than 1 billion years old. According to our current understanding, black holes form from the collapse of massive stars, starting out at only a few tens of solar masses. From there, they grow by feeding on surrounding gas and occasionally merging with other black holes. But there is a natural speed limit to this growth known as the Eddington limit. It's like trying to drink from a fire hose. There's only so much matter a black hole can swallow at once before the intense radiation it emits pushes the rest of the material away. This throttles the growth process and ensures that black holes cannot become monsters overnight. By every calculation we've made, it should take billions of years for a stellar mass black hole to grow into a supermassive one. Yet Webb has shown us black holes in the early universe that dwarf even the largest found in galaxies like the Milky Way, reaching masses of 10 billion suns when the cosmos was barely old enough to form its first stars. To understand how shocking this is, imagine a newborn baby that weighs more than a fully grown adult within its first year. The timeline doesn't just stretch, it breaks. For these black holes to exist so early, they would have had to feed continuously at or near their maximum possible rate from the instant they formed, with no interruptions and no downtime. Yet the environment of the early universe should have been hostile to such growth. Gas clouds were turbulent, stellar explosions were rampant, and galaxies were still chaotic in their infancy. Under these conditions, black holes should have starved, unable to feed steadily enough to balloon into giants. Instead, what Webb reveals are cosmic behemoths already thriving at the dawn of time. One of the most staggering examples is a quasar powered by a black hole 10 billion times the mass of the Sun, blazing less than a billion years after the Big Bang. This single object contains more mass than many entire galaxies from that era, and it's actively devouring material at a rate that floods the universe with light. These quasars shine so brightly they can outshine their host galaxies, making them some of the most luminous objects in existence. But here's the paradox. The very process of feeding should also blow away the fuel supply needed to keep growing. As matter spirals into the black hole, it heats up and emits intense radiation that blasts outward, disrupting the surrounding gas. That means feeding at such high rates should have shut down the growth process long before these black holes reached their impossible sizes. The presence of these supermassive black holes creates a chicken and egg problem. Did galaxies form first, creating the conditions that allowed black holes to grow so rapidly? Or did black holes form first, acting as gravitational anchors around which galaxies assembled? Both scenarios demand processes that are far faster and more efficient than anything we've observed in the present-day universe. Some scientists propose that these black holes didn't start small at all, but rather formed directly as massive objects in the earliest moments of cosmic history, bypassing the need to grow from stellar corpses. Known as direct collapse black holes, these hypothetical giants could have formed from huge gas clouds collapsing under their own gravity without fragmenting into stars first. Others push the idea further, suggesting the existence of primordial black holes, objects born not from stars, but from the extreme conditions of the Big Bang itself. If true, these black holes would have been seeded at the very birth of the universe, ready-made gravitational monsters that could explain why Webb sees them so early. But even these theories don't fully explain how such massive black holes could exist in galaxies already teeming with stars. Feeding a black hole should choke off star formation, yet Webb shows us both happening simultaneously, galaxies blazing with billions of stars, while their central black holes gorge themselves in defiance of every known rule. This paradox forces cosmologists to confront a troubling possibility that our models of black hole physics are incomplete, or that the early universe followed rules fundamentally different from the ones that govern it now. These ancient monsters suggest that the cosmos may have shortcuts to growth and organization that we simply don't yet understand. And if supermassive black holes were already fully formed so early, then the story of how light first emerged in the universe takes on an even stranger and more unsettling twist, because the next mystery Webb uncovered is that brilliant blue light sources were shining at a time when stars shouldn't have existed at all. Just when astronomers thought the discoveries of impossibly massive galaxies and supermassive black holes were enough to challenge our entire understanding of the universe, the James Webb Space Telescope uncovered something even stranger: mysterious sources of bright ultraviolet light shining from an era when stars shouldn't have existed yet. These light sources were detected at redshifts as high as 25, which corresponds to a time only about 100 million years after the Big Bang. According to everything we know about cosmology, that should have been far too early for stars, galaxies, or any organized light sources to form. The universe at this point was supposed to be a dark, hot, chaotic expanse, still recovering from its violent birth. Matter was largely hydrogen and helium gas, still too energetic to collapse into the dense, cool pockets needed for nuclear fusion to ignite. And yet, Webb's infrared eyes detected the unmistakable glow of blue, ultraviolet light pouring from objects that simply shouldn't exist. To appreciate how shocking this is, consider the timeline predicted by standard cosmology. After the Big Bang, the universe went through a cooling period where atoms formed and light could finally travel freely. About 380,000 years later, then came the so-called cosmic dark ages, a long stretch of hundreds of millions of years where no stars had yet ignited to light up the cosmos. Only after enough matter clumped together under gravity and cooled could the first stars, population 3 stars, be born. These stars, predicted to be massive, short-lived and composed of only hydrogen and helium, were supposed to blaze into existence around 300 to 400 million years after the Big Bang, marking the cosmic dawn. But Webb's detection of bright ultraviolet light from only 100 to 200 million years after the Big Bang shatters this carefully constructed timeline. It suggests that cosmic dawn may have begun almost immediately, with stars or something equally luminous existing much earlier than we thought possible. The question then becomes, what exactly are these mysterious light sources? At first glance, their brightness and spectrum resemble that of hot, massive stars. That would imply that star formation began astonishingly early, long before conditions should have allowed it. Imagine trying to light a bonfire in a storm while the wood is still soaking wet. It shouldn't be possible, yet somehow the fire roars to life. These objects shine with the intensity of organized stellar populations when the universe should still have been too hot and turbulent for stars to form at all. But astronomers are also considering more exotic possibilities. Some of these light sources appear point-like rather than extended, suggesting they might not be clusters of stars, but individual compact objects. This has led to speculation that they could be primordial black holes, hypothetical entities that may have formed directly out of density fluctuations in the earliest fractions of a second after the Big Bang. If these primordial black holes were surrounded by gas, the material falling into them would generate intense ultraviolet and X-ray radiation, mimicking the appearance of star clusters. The implications of such a discovery are staggering. If primordial black holes exist, and were numerous in the early universe, they could help explain several of Webb's impossible findings. They would provide ready-made gravitational anchors for galaxies to form around, bypassing the slow process of dark matter halos clumping together. They could also produce the incredible luminosity required to realize the universe much earlier than expected, solving the mystery of how cosmic fog was cleared away so quickly. Even more provocatively, they could represent a form of dark matter, explaining not only the strange early light sources, but also one of the deepest mysteries of modern physics. Yet the story doesn't end there. Some of the mysterious ultraviolet sources might not be stars or black holes at all, but entirely new classes of cosmic objects. Their brightness, size, and distribution don't always match predictions for any known type of structure. It's as if Webb has caught glimpses of phenomena that belong to a universe governed by different rules, peeking into a reality that doesn't line up with our physics. For cosmologists, this creates an unsettling paradox. If stars could exist earlier than physics allows, then maybe the laws of cooling, gravity, and fusion operated differently in the primordial universe. If they weren't stars, then we might be seeing evidence of exotic phenomena that no one has even theorized yet. Either explanation forces a radical rethinking of the story of cosmic dawn. What makes these discoveries even more compelling is how they tie directly into other mysteries Webb has revealed. The same impossibly massive galaxies that appeared too early could have been powered by these mysterious light sources, whether they were hypergiant stars, direct collapse black holes, or primordial black holes. The same ultraviolet radiation that created vast ionized bubbles around young galaxies could have originated from these strange objects. Everything is connected, and the deeper Webb looks, the more the entire cosmic timeline seems to collapse under its own contradictions. The existence of these ultraviolet light sources at such extreme redshifts challenges not just the details of cosmology, but the very framework we use to understand the universe. If light could blaze forth so early, then the dark ages we believed lasted for hundreds of millions of years may never have existed at all. Instead of a silent, empty cosmos waiting patiently for its first stars, the universe may have burst into light almost immediately, leaving us with a picture of reality that is far more dynamic, violent, and strange than we ever imagined. And if that's true, then the next puzzle Webb uncovered, the impossibly short timeline of galaxy formation, becomes an even greater paradox that scientists are scrambling to solve. One of the most profound mysteries revealed by the James Webb Space Telescope is the problem of time itself, the timeline paradox that shows galaxies forming, growing, and organizing billions of years faster than our theories say should be possible. In the standard model of cosmology, the early universe after the Big Bang was hot, dense, and chaotic. Gas clouds had to cool, dark matter had to clump together into halos, and the first stars had to live, die, and scatter heavy elements before galaxies could truly begin to assemble into large, structured systems. Every step in this process has a natural timescale built into the laws of physics, and those timescales add up to billions of years before massive, mature galaxies like the Milky Way should appear. Yet Webb's deep field images reveal enormous, fully formed galaxies shining just 600 to 700 million years after the Big Bang. They are not small, fragile collections of a few stars. They are colossal cities of light, containing hundreds of billions of suns, organized into complex structures as if they had been evolving for eons. To grasp the impossibility of this, think of building a massive metropolis. First, you must lay down the infrastructure: roads, utilities, foundations, then houses rise, then skyscrapers, and finally the city matures with layers of culture, commerce, and history. In the universe, this infrastructure is dark matter halos, which provide the gravitational scaffolding. The houses and skyscrapers are stars and galaxies, which take shape only once the scaffolding is strong enough. According to physics, this construction process should take billions of years. But what Webb is showing us is that the cosmic city was already thriving only a few 100 million years after the Big Bang. It's like finding a modern New York City on Earth just a century after humans discovered fire. The problem isn't just that galaxies formed faster than expected, it's that they seem to have skipped entire stages of development. The models predict galaxies should start small and chaotic, merging slowly over time into the giants we see today. Instead, Webb is seeing massive galaxies right out of the gate, and in some cases their stellar populations already appear old, as if they had gone through multiple generations of star formation and chemical enrichment. The presence of heavy elements like carbon, oxygen, and iron in these galaxies adds another layer of contradiction, because those elements require stars to live and die first. That cycle should take hundreds of millions, if not billions of years, yet here they are, fully present in galaxies that existed when the universe was only 3% of its current age. Scientists describe this as a crisis in cosmology. because no simple tweak to existing models can stretch the timeline enough to accommodate these galaxies. The discrepancy isn't minor, it's off by a factor of 3 or more. If galaxies can grow to 100 billion solar masses in less than a billion years, then either the universe is older than we think, or some unknown process accelerated galaxy formation to impossible speeds. Some suggest that primordial black holes or direct collapse black holes could have seeded galaxies, giving them a gravitational head start. Others speculate about exotic physics, like dark matter, that behaves differently in the early universe, or even changes in the fundamental constants of nature. But each explanation opens up new questions, often clashing with other well-established observations. The timeline paradox extends beyond individual galaxies. It also affects cosmic structures on larger scales. Webb has revealed that galaxies were already organized into filaments and clusters in the early universe, structures that should require billions of years of gravitational interactions to take shape. This level of organization is another impossibility, hinting that the universe either evolved much faster in its early stages, or that our concept of time in cosmology is flawed. Some researchers even revisit radical alternatives, such as tired light theory or models, where the universe has no real beginning, but cycles endlessly, providing far more time for structures to develop. The most unsettling part of the timeline paradox is its consistency. It's not one rogue galaxy that could be explained as a fluke or measurement error. It's a pattern across multiple observations, using independent methods, confirmed by different research teams. The James Webb Space Telescope has forced cosmologists into a corner: either rewrite the timeline of the universe, or accept that the fundamental physics we thought we understood is incomplete. And if galaxies really did form this quickly, then the efficiency of star formation in the early universe must have been far higher than anything we observe today. This opens the door to the next great puzzle. How could these galaxies convert almost all of their raw gas into stars with near-perfect efficiency, defying one of the most basic limits of astrophysics? The timeline paradox naturally leads us into another equally perplexing discovery from the James Webb Space Telescope: the efficiency problem. In the modern universe, galaxies form stars at a relatively modest pace, converting only about 10% of their available gas into stars before stellar winds, supernova explosions, and other feedback mechanisms blow the remaining gas away or heat it so much that it cannot collapse again. This inefficiency is not an accident, it is a fundamental aspect of physics. Stars burn, explode, and disrupt their environments, ensuring that galaxies never become perfectly efficient factories of light. But Webb's revelations suggest that early galaxies were somehow operating on an entirely different level, pushing star formation close to 100% efficiency, something thought to be physically impossible. If true, it means that the early universe had rules that were either dramatically different from today, or that we have misunderstood the most basic aspects of how stars and galaxies are built. Imagine trying to run a factory where you use every single scrap of raw material with zero waste. In our everyday world, that is impossible. Some materials always get lost, burned off, or recycled inefficiently. Yet the early galaxies Webb has detected seem to have achieved exactly that. They appear to have taken nearly all of their primordial gas and rapidly transformed it into blazing stellar populations. This kind of efficiency would require conditions that neutralize or suppress every disruptive process we know of. No stellar winds powerful enough to push gas away, no supernovae tearing apart the surrounding medium, no turbulence to scatter gas clouds, and no radiation pressure to slow star formation. Every single atom of gas would have to collapse and ignite in record time, something that contradicts the very limits astrophysicists thought were built into the universe. One explanation put forward is that star formation in the early universe was bursty, meaning it happened in short, intense episodes where galaxies lit up with furious starbirth before going quiet again. During these bursts, perhaps conditions allowed for unusually high efficiency, compressing millions of years of stellar activity into cosmic moments. But even this does not fully explain the sheer size and brightness of the galaxies Webb has uncovered. The luminosity of these galaxies suggests sustained, not temporary, star formation, and at levels far beyond what burst models predict. To produce the billions of stars necessary, the early galaxies would still need to have operated at or near maximum efficiency for extended periods of time. Some theorists have suggested that the physics of star formation itself may have been different in the early cosmos. Population 3 stars, the first generation of stars born from pure hydrogen and helium, are thought to have been more massive, hotter, and shorter-lived than stars today. If true, these stars could have collapsed quickly, exploded, and enriched their galaxies with heavier elements at an accelerated pace, allowing new stars to form rapidly. But while this could speed things up somewhat, it still does not solve the efficiency problem entirely, because even massive stars create feedback, blasting gas away with their radiation and explosions that should slow down star formation overall. Another proposal is that dark matter played a greater role than expected, funneling gas more effectively into galaxies and trapping it in deeper gravitational wells that made it harder for feedback to disperse. This could, in theory, allow galaxies to retain more gas and sustain high-efficiency star formation. But again, the timescales remain too short and the required efficiency levels too high to fit neatly into even modified versions of these models. Some researchers go further, proposing that the early universe might have operated under different physical constants, or that exotic forces helped suppress feedback, essentially rewriting the rules of astrophysics during the universe's first billion years. The efficiency problem is not a minor detail. It goes to the very heart of how stars, galaxies, and eventually life itself came to be. If galaxies could convert nearly all of their raw gas into stars, then the early universe must have been far more active, luminous, and structured than we imagined. It also forces us to rethink the concept of cosmic limits, those boundaries of what is possible in nature that we once assumed were unbreakable. Webb has shown us that those limits may not have always applied, or that they are far more flexible than we believed. This puzzle is not isolated either. It connects directly with other paradoxes: the rapid appearance of heavy elements, the existence of massive black holes at impossibly early times, and the large-scale organization of galaxies when the universe was still in its infancy. All of these anomalies point toward one unsettling conclusion: that the early universe was not playing by the rules we see today. If the efficiency of early galaxies really was near perfect, then it opens the door to even stranger questions. What if energy production itself, the process of stars shining, was operating differently? What if galaxies had access to mechanisms beyond nuclear fusion as we understand it? These questions set the stage for the next great cosmic enigma: the black holes at the hearts of these early galaxies, monstrous objects that should not exist, but do, feeding and growing when the universe was still barely a child. At the center of many of the James Webb Space Telescope's most puzzling discoveries lies a problem even more staggering than galaxies forming too quickly or stars being born too efficiently: the existence of supermassive black holes in the early universe. These are not small stellar remnants or modest black holes a few times the mass of the Sun. These are titans, billions of solar masses, lurking in galaxies that existed less than 1 billion years after the Big Bang. According to everything astrophysicists thought they knew, these objects simply should not exist at such an early stage of cosmic history. To understand why, we must first recall how black holes are supposed to form. Typically, a massive star ends its life in a violent collapse, leaving behind a black hole a few times to perhaps 100 times the mass of the Sun. From there, these stellar black holes can grow by consuming surrounding gas and merging with other black holes. But this process is slow and capped by a natural limit called the Eddington limit. This limit acts like a cosmic throttle, restricting how fast a black hole can grow. When a black hole feeds, it generates so much radiation that it pushes away additional matter, preventing runaway growth. Even if a black hole fed continuously at this maximum rate, it would take billions of years to reach the size of the giants we see today. The problem is that Webb has already detected these giants when the universe was not even a billion years old. Take one of the most shocking examples: a quasar discovered by Webb that contains a black hole weighing around 10 billion times the mass of the Sun. To put this into perspective, our own Milky Way's central black hole is about 4 million solar masses, and it has had more than 13 billion years to grow. Yet here is an object billions of times larger appearing when the universe was barely in its infancy. It is like finding a fully grown elephant in a nursery where only newborn mice should exist. The time simply doesn't add up. If these black holes started as remnants of the first stars, there wasn't enough time for them to eat their way into becoming cosmic monsters. Even if they had a head start, the Eddington limit should have slowed them down. This paradox has led scientists to consider more exotic possibilities. One is that these early black holes did not start small, but were instead born large. Theories of direct collapse black holes suggest that under certain conditions, vast clouds of primordial gas could collapse directly into black holes, weighing tens of thousands or even hundreds of thousands of solar masses without first forming stars. Such massive seeds would make it easier to reach billions of solar masses in under a billion years. But the conditions required for this to happen are supposed to be rare and extremely specific, involving low metallicity, strong radiation fields, and precise collapse dynamics. Webb's discoveries suggest that if this mechanism is real, it must have been far more common than anyone imagined. An even bolder idea is that some of these early black holes are primordial in origin, forming directly from density fluctuations in the first fractions of a second after the Big Bang. Unlike stellar black holes, which require stars to die first, primordial black holes could have existed from the very beginning of cosmic time. They would have acted as ready-made seeds, instantly able to start gathering matter and growing into supermassive monsters. If this is true, it would radically reshape our understanding of both cosmology and particle physics, since primordial black holes would be tied to unknown physics in the very first instance of the universe. The existence of these early giants also creates another problem. Black holes do not just sit quietly at the centers of galaxies. When they feed, they unleash tremendous amounts of energy, creating quasars, objects so bright they can outshine their host galaxies. This energy should blow away the very gas that galaxies need to form stars, choking off growth. Yet Webb shows us galaxies where black holes and stars are both thriving together, somehow feeding and shining without interfering with one another. It is like watching a firestorm rage in a forest without burning down the trees. The balance seems impossible under known physics, but it is happening nonetheless. What these discoveries imply is that either black hole growth can somehow bypass the Eddington limit, or our understanding of how matter behaves in extreme conditions is incomplete. Some researchers speculate about episodes of super Eddington accretion, where black holes might feed faster than theory allows under special conditions. Others suggest exotic forms of matter, new particles, or even altered laws of gravity in the early universe. Whatever the answer, these monstrous black holes are rewriting the rules of cosmic evolution. The presence of such impossibly massive objects so early in cosmic history forces us to confront an unsettling possibility. Perhaps the universe did not evolve gradually as we believed, but instead leapt ahead in ways we cannot yet comprehend. If black holes existed from the start, or if they could grow in ways we do not yet understand, then the entire story of galaxy formation, star birth, and cosmic history must be reconsidered. The mysteries do not end here, though. Beyond the black holes, Webb has revealed strange light sources and mysterious objects in the deepest reaches of time, objects that shine when stars themselves should not yet exist. If the discovery of impossibly massive galaxies and supermassive black holes in the early universe left cosmologists reeling, what came next pushed the boundaries of what could even be imagined. The detection of mysterious light sources that appeared far earlier than any stars or galaxies should have existed. The James Webb Space Telescope, with its extraordinary infrared vision, captured faint yet distinct points of light, shining from a time when the universe was only 100 to 200 million years old, an era that should still have been dark, empty, and chaotic. According to the standard model of cosmology, the universe underwent a dark ages phase after the Big Bang. Once hydrogen and helium atoms formed around 400,000 years after the beginning, the universe was filled with a neutral fog of gas that blocked light. Gravity slowly began pulling matter together, but the process was expected to take hundreds of millions of years before the first stars ignited, ushering in the so-called cosmic dawn. Webb, however, shattered this timeline. Instead of darkness, it revealed bright ultraviolet light from objects that should not exist for another few 100 million years. These enigmatic sources shine with the energy signature of massive, hot stars, blazing blue and bright in wavelength that cut through the cosmic fog. But if stars were already burning this early, it means the dark ages were far shorter than theory predicts, or perhaps never really happened at all. This is a profound challenge to Big Bang cosmology, because the dark ages are considered a crucial step in the universe's evolution. Without this long pause, the expected slow buildup of structure collapses, and the timeline compresses to levels that defy physics as we know it. Imagine planning for a construction project that should take a century to complete, only to arrive and find the skyscraper finished after a few years. That is what Webb's observations imply about the first luminous object. Some researchers argue that these sources might not be normal stars at all, but something far stranger. A fraction of them appear point-like, not extended like galaxies, suggesting they could be primordial black holes, radiating light as they consume matter. If true, this would align with the idea that some black holes formed directly out of the earliest conditions of the universe, bypassing stars altogether. Others suggest that what Webb is detecting could be exotic forms of stellar populations, perhaps population 3 stars, the first theoretical stars composed purely of hydrogen and helium. These would have been far more massive and luminous than modern stars, capable of burning with astonishing brightness before dying in violent explosions that seeded the cosmos with heavier elements. The problem is that even population 3 stars need time to form from collapsing gas clouds, and the gas at 100 million means after the Big Bang should still have been too hot and chaotic to collapse efficiently. The sheer luminosity of these early sources is another puzzle. To shine so brightly, they must either contain more mass than theory allows for such an early epoch, or produce energy through mechanisms we have not yet discovered. Their ultraviolet light is so intense that it likely contributed to regionizing the surrounding hydrogen gas, making the universe transparent much earlier than expected. In fact, the size of the ionized bubbles around these sources suggests they were pumping out vast amounts of energy into their environments, clearing away fog across millions of light-years of space. This rapid regionization compounds the mystery because it requires a level of organization and energy production that seems impossible in the young, supposedly primitive universe. To explain these anomalies, cosmologists have floated radical possibilities. Perhaps the laws of physics themselves were slightly different in the early universe, allowing matter to collapse and ignite much faster than expected. Or perhaps we are misinterpreting what we are seeing entirely, and these are not early stars or galaxies but some unknown class of object. Some theories even suggest that new forms of exotic matter or energy could be powering these light sources, acting as engines of illumination outside the framework of normal nuclear fusion. If primordial black holes or exotic stellar populations are indeed responsible, then these discoveries may offer the first direct evidence that the universe's infancy operated under a set of rules very different from the ones we observe today. The implications are staggering. If the universe was already alight with stars, black holes or exotic objects just 100 million years after the Big Bang, then our carefully constructed cosmic timeline is fundamentally flawed. The Dark Ages may never have existed as we imagined. Instead of a long, slow wait for the first light, the cosmos may have burst into activity almost immediately, challenging every assumption about how structure forms and evolves. These early light sources are not just curiosities, they are cosmic signposts pointing toward a reality where time, formation and energy unfolded far more rapidly and strangely than we ever thought possible. And as astonishing as these revelations are, they lead directly into an even deeper mystery, the timeline problem itself, where every step of cosmic evolution seems compressed into impossibly short intervals that no conventional theory can reconcile. One of the most unsettling revelations delivered by the James Webb Space Telescope is the collapse of the cosmic timeline, a problem that has rapidly evolved into a full-blown crisis in cosmology. For decades, scientists believed they had a clear sequence for how the universe developed. First came the Big Bang, followed by hundreds of millions of years of darkness. Then the gradual cooling of gas into stars, the slow buildup of galaxies, and finally the emergence of the vast cosmic structures we see today. But Webb has forced us to reconsider this neat chronology by showing us galaxies, stars, and black holes forming far earlier, faster, and more efficiently than any model allows. The timeline, once thought to stretch gracefully across billions of years, has been compressed into just a fraction of that span. The implications are staggering because this doesn't just challenge specific aspects of astrophysics, it threatens the foundation of the entire Big Bang model. Consider the galaxies Webb has detected that existed just 500 to 700 million years after the Big Bang. By all accounts, they should not have had enough time to assemble into such massive, organized systems. Building a galaxy is not instantaneous. It requires the gradual clumping of dark matter into halos, the cooling of gas into stars, the deaths of those stars to enrich the environment with heavier elements, and the recycling of that material into subsequent generations. Each of these stages takes time, millions, even billions of years, yet Webb has found galaxies that are already rich with heavy elements, containing dust and metals that require several stellar life cycles to produce. It is like discovering an oak tree with deep roots and a full canopy in a garden where the seeds were planted yesterday. The clock is broken, and the standard timeline no longer makes sense. This problem is not confined to galaxies. Stars themselves appear to have formed much earlier than predicted. The universe was supposed to endure a prolonged Dark Ages phase, Yet Webb's images of luminous blue light from redshift 17 and even redshift 25 suggest that star formation was already underway just 100 to 200 million years after the Big Bang. That is at least 3 to 4 times earlier than expected. And these are not dim, struggling stars. They are bright, massive, energetic objects blazing so fiercely that they likely reionized large sections of the surrounding universe. If stars could form this quickly, it means the process of gas cooling, collapsing, and igniting nuclear fusion operated on an impossibly accelerated schedule. The black holes deepen the paradox even further. To grow to billions of solar masses within less than 1 billion years requires sustained, near-perfect feeding at or above the theoretical maximum allowed by physics. Yet Webb has already revealed quasars with supermassive black holes weighing 10 billion suns when the universe was still an infant. This collapses billions of years of expected growth into a few hundred million, requiring either entirely new processes of black hole formation or new physics altogether. Primordial black holes, direct collapse scenarios, or super Eddington feeding have all been proposed, but none of these ideas sit comfortably within the framework of the Standard Model. Even the universe's expansion rate contributes to the timeline crisis. Local measurements give us one speed, while early universe measurements from the cosmic microwave background give us another, creating the so-called Hubble tension. Webb's data has leaned toward confirming the faster rate, which means the universe may be younger than we think, or that it evolved more rapidly in its early years. Either way, the discrepancy compounds the already impossible schedule of cosmic evolution. If the universe had less time than we assumed, then the early galaxies Webb discovered are even more inexplicable. Everywhere Webb looks, the same story emerges. What should take billions of years is happening in mere hundreds of millions. Galaxy formation, chemical enrichment, black hole growth, star birth, reionization, all are occurring at speeds that cannot be reconciled with our physics. This is not a matter of fine-tuning or small errors. It is a systematic collapse of the timeline that spans across multiple independent observations. It is as if the universe pressed fast forward on its own evolution, leaping through steps we thought were unskippable. The consequences of this realization are profound. If the timeline is broken, then either the Big Bang happened differently than we thought, or the laws of physics operated differently in the past. Perhaps dark matter clumped faster, gas cooled more efficiently, or stars ignited under conditions we cannot yet replicate. Or perhaps our most cherished assumption that the redshift of light corresponds directly to time and distance is itself flawed. Alternative models like tired light, variable constants, or even primordial cosmic states before the Big Bang are now being discussed more seriously than ever before. The timeline crisis forces us to confront a universe that seems unwilling to wait for our theories to catch up. Instead of a slow, steady evolution, Webb is showing us a cosmos that assembled itself in a hurry, defying every prediction. What this means for cosmology is still uncertain. But one thing is clear, our cosmic calendar must be rewritten from the ground up. And as shocking as this compression of time may be, it leads us into another equally troubling discovery, how the very structure and organization of the early universe seem impossibly advanced for such a young age. The James Webb Space Telescope has done more than capture breathtaking images of distant galaxies. It has shaken the very foundations of how humanity understands its place in the cosmos. For decades, cosmology has relied on a story that seemed solid. The universe began 13.8 billion years ago with the Big Bang, expanded and cooled, and gradually built stars, galaxies, and black holes over billions of years. This narrative filled textbooks, won Nobel Prizes, and offered a sense of clarity to questions about our origins. But Webb's discoveries have ripped through that certainty, leaving us standing at the edge of a vast unknown. What was supposed to be the ultimate confirmation of the Big Bang has instead become its greatest challenge. The telescope has revealed impossibly massive galaxies forming just a few 100 million years after the Big Bang, black holes so large they shouldn't exist in the time available, stars blazing during epochs when the universe should still have been dark, and structures organized with a maturity that mocks our carefully crafted timelines. Each revelation compresses billions of years of expected evolution into impossibly short spans, forcing us to reconsider not just details, but the entire framework of cosmic history. The conclusion we are left with is unavoidable. The universe is not behaving according to the rules we thought we understood. Every image Webb sends back deepens the mystery, showing us galaxies filled with heavy elements long before they should exist. Quasars powered by black holes that grew faster than physics allows, and light sources shining during a period when the cosmos was supposed to be silent. These aren't minor discrepancies or anomalies to be brushed aside. They are systematic, consistent, and dramatic contradictions that strike at the heart of our cosmological models. When the same problem appears across multiple types of observations, mass, age, brightness, chemical composition and structure, it is no longer possible to claim coincidence. It is evidence that our theories are missing something fundamental. This does not mean the Big Bang is completely wrong, but it does mean it is incomplete. Perhaps the universe really did begin with an explosive event, but the processes that followed unfolded very differently from what we assumed. Maybe there were mechanisms at work in the early cosmos, primordial black holes, exotic particles, variable laws of physics that no longer operate today, leaving behind only their mysterious fingerprints. Or perhaps the very way we measure cosmic time and distance, by interpreting redshift as an indicator of expansion, is flawed. Ideas like tired light or variable constants, once dismissed as fringe, are being reconsidered as possible solutions to the timeline crisis Webb has exposed. The conclusion also points toward a humbling truth. Science is not a finished book, but an evolving story. For all our advancements, humanity may still be in the earliest chapters of understanding the cosmos. Webb has reminded us that the universe is stranger and more complex than any model can yet capture. Instead of despair, this should ignite curiosity. Every impossible galaxy and every premature star is not just a problem, but an invitation to expand our imagination and pursue new frontiers of physics and cosmology. It may be that the universe is far older than we thought, or that time itself behaves differently on cosmic scales. It may be that unseen forces shaped the first billion years in ways we have yet to comprehend. Whatever the answer, one thing is clear: we are living in a revolutionary moment where old certainties collapse and new possibilities emerge. As we draw a conclusion from Webb's discoveries, it is not one of finality but of beginning. The telescope has not closed the book on cosmic origins. It has ripped the pages apart and challenged us to write a new story. This new narrative will likely demand bold ideas, radical theories, and a willingness to accept that our understanding of reality may have been only a fragment of the truth. The impossible galaxies, stars, and black holes Webb has shown us are not just anomalies. They are cosmic signposts, pointing toward a deeper order of reality we have yet to uncover. And as unsettling as this may be, it is also exhilarating because it means the greatest discoveries are still ahead. The universe has revealed itself to be faster, brighter, and more mysterious than we imagined, and in that revelation lies the greatest gift of science, the realization that the quest for truth is never over.